Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. In the last class we started looking at schemes for nonlinear problems, and we started looking at multi-step schemes, and we saw two schemes. One is the two-step Lax-Van-Draaf, okay, and second was Richtmeier, okay, and both the schemes use two steps. One is basically the Lax-Frederick and second is leapfrog. Okay, this in the two-step Lax-Van-Draaf, you do the calculation at I plus half and so on and so forth. Here you do at I. Okay, and we saw that when you combine both the steps for a linear problem, you basically get a Lax-Van-Draaf type of scheme. Okay. Today we will look at the McCormick scheme. Okay, this is also a multi-step scheme, and this is very popular in the CFD community. In fact, when you start solving, let us say Euler's problem for a nonlinear problem, let us say the sock tube and other problems, the first scheme of your choice will be the McCormick scheme. Okay. So, like the Richtmeier or the two-step Lax-Van-Draaf, McCormick also has two steps. Okay. So, this is more simpler than that. So, in this you will basically use first the forward differencing and then use the backward differencing. Okay. And you can actually do the opposite. You can first have the backward differencing and then have the forward differencing. It does not change anything. Okay. So, let us look at this McCormick scheme. Okay. So, we have the predictor step, okay, which is basically the forward differencing, or you can use the backward differencing. Okay, and we will use it for, so you can get ui star will be ui. So, star is nothing but my predictor step. So, I am calling it this is n plus 1. Okay. But this is a predictor. So, maybe you can do it right, n plus 1 bar, okay, minus delta t by delta x, and this is basically you are using the forward step first. So, this is ui plus 1 n minus ui n. Okay. So, this is your predictor step, and then you go the corrector step, okay, but with the step of delta 2 by 2, okay, and this will be backward differencing. Okay. So, if you do the backward differencing, so this will be ui n plus 1 minus ui, now we are doing it delta t by 2, this will be n plus half, right, by delta t will be equal to minus c, and we are doing the backward differencing. So, that will become ui n minus ui minus 1 n by delta x, right, and this will use the value at we calculated earlier, ui star and ui minus 1 star. Okay. And how do you get this ui n plus half? Ui n plus half will become half of ui n plus ui star. Okay. So, you have calculated this ui star, which is basically it is like n plus half bar. Okay. So, we want to get the value at n plus half. So, this is basically delta 2 by 2, right. So, this is ui plus ui star. So, ultimately your scheme will become ui n plus 1 will be half ui n plus ui star, which is the predictor value, minus lambda by 2. Okay. This is ui star minus ui minus 1 star, okay, which we have predicted earlier. Okay. So, this scheme these two steps are called the McCormick scheme. Okay, and if you combine both of them, go back and try this, this will give you the Lax-Van Derf scheme. Okay, and because of that, it will have the same property as the Lax-Van Derf. So, this will be stable for lambda less than equal to 1, and accuracy is delta x square delta t square. Okay, and as I told earlier, you can also do first step is the backward differencing. Okay, so that will be u I star, it will be u I n minus c delta t by delta x, u I n minus u I minus 1 n. Okay, and then you do the forward differencing, but with time step delta t by 2. Okay, so your final value u I n plus 1 will become half u I n plus u I star, okay, minus lambda by 2. Now, use the forward differencing, this is u I plus 1 star minus u I star. Okay, both are equivalent. Okay, so same thing is shown here. Okay, so this is how you can get, and this is a stable lambda or sigma less than equal to 1. Okay, so this is also a second order method, P is equivalent to Lax-Van Derf. You can alternate these two. The advantage of this is no need to store values, so you do not need like I plus half and I minus half and so on and so forth. Okay, and this works well for the nonlinear problems. Okay. So, with that we have basically discussed several schemes in the last few classes, and let us look at how these schemes behave, okay, practically on many different problems. Okay, so, I will be taking 3 examples. One is the function which is like an exponential function. So, this is like e to the power minus x minus some value x0 square. Okay, so, if the x is less than x0, this is basically decaying, otherwise it is increasing. Okay, so that is one exponential function. I will look at the sine function. Okay, and then I will also look at the step function. Okay, why step function? Because you know that there is a discontinuity here, and as we have seen that you might get some wiggles there. Okay, and we will check it for the linear problem and the nonlinear problem. Okay, so I will take you to MATLAB online, but you can also use your favorite coding tool. You might use Python, you might use C, C++, Fortran, whatever you want, and you can just try out these schemes and see how it works. Okay, so let me take you through some examples. You can, if you have a standalone MATLAB, that also you can use, and there are 2 ways to use the MATLAB. I mean, you can do the coding as a script, which is .m file, and you can also do the lib script, basically where what you can do is you can basically write your equation and see, I mean, for your future you can try it. And I am showing you some examples here, but you should really try it out. Okay, you should write these codes, and these are not very difficult codes. Okay, so I hope you are able to see the screen. Okay, so I am solving this linear convection problem. Okay, which is basically del u by del t plus c del u by del x equal to 0. Okay, let me just make a little big. Okay, and so the convection speed, this is the convection speed. So this can change. Okay, so I am using 0.5 now, but you can use different values, and this is the initial function, which is exponential minus x minus 2 square. So if you can see that if it initially if it is x less than 2, okay, then it is basically growing, otherwise it will be decaying, because there is a negative sign here. If it is negative minus sign, then it will be growing, otherwise it will be decaying. Okay, okay, and for this the analytical solution will be x minus ct. So as you know that for the linear problem, del u by del x plus c del u by dt plus c del u by del x, and if the function u is equal to, let us say, f x, the solution will be f x minus c t. So that we have discussed while we are talking about the characteristic of the equation. Okay, so you can just replace this initial solution with, and instead of x you put x minus c t, that will give you the analytical solution. So we will compare those solutions, and this is the intervals that I have chosen. L equal to, this is the length, total length, delta x, delta t, this is the convection velocity and amount of time steps. Okay, so let us look at, I have couple of more problems, okay, but let me just do it for this problem first. Okay, so these are the parameters that you can define. L equal to basically 10, delta x equal to 0.1, and then x 0 to dx delta L. Let me just run this for you once. Okay. Okay, so now it is running. You can see that it's showing busy, so that's because it is running. Okay, yeah. So let me just stop it here. Okay. Yeah, so you can see that because I've used the x, so this you can use the linear space, or you can use 0 to dx to L. So I've chosen dx equal to 0.1. Okay, so the x will be 0 to 10, it will divide in the steps of 0.1. So this is the value of x will be like this. Okay, these are the values. Okay, and then I've taken dt equal to 0.1. Okay, so if you choose like this, so your CFL number, which is lambda, is c dt by dx. So that will become 0.5, right, because c is 0.5, dt is 1, 0.1 and dx is 0.1. So your lambda, okay, you can just see it here, is equal to 0.5. So this is less than 1. So the most of the schemes should be stable, okay, except the FTCS. Okay, and this is just the definition that I want the 0 of size length x, and this is my initial function. Okay, and now I have written the code for different schemes. Okay, so here you can see this is the operand scheme, c delta t by del x, ui minus 1 n. So I am using c delta t by del x equal to lambda, my lambda. But this is very simple code. Go from 2 to length of u, basically the total size. Okay, why am I starting from 2? Because it takes the value of I minus 1, right. So it cannot go to I equal to 0, right. The MATLAB starts from 1, right. So I am taking from 2. So that means you need boundary conditions at basically you need boundary conditions at both the sides. Okay, so here I am using a periodic boundary condition. I actually you do not need to do that, because I am not letting the wave convect and come back again. I am limiting myself to the point where it has not touched the either boundary. Okay, but you can use a periodic boundary condition and it can continue going. Okay, similarly this is the central differencing scheme, okay, which is c delta t by 2 delta x, and the function name is central here. I calculate lambda, and this is 0.5 into lambda u I plus 1 and u I minus 1, right. This is Lax-Frederick scheme, okay, which is the uin term is replaced by half of ui plus 1 and ui minus 1. So I have just replaced this term here, okay, and all other terms basically remains the same. Okay, this is the Lax-Frederick scheme. Okay, Lax-Frederick scheme where you are adding the dissipation term here. So this alpha is basically equal to lambda square, right, for the Lax-Frederick, but I have used the general alpha value. Okay, we will see what happens if you increase the value of alpha, and how the schemes becomes more and more dissipative. Okay, so these are the 4 schemes implemented here. Now let us do it one by one. Okay, so first I am trying to do it for, okay, let us do it for the central scheme. Okay, so let me call that. Okay, do have upwind. So yeah, let me do the upwind scheme first. Okay, okay. So let me run that. Yeah, so you on the right hand you can basically see how things are growing. Okay, I hope you are able to see the movie. Okay, so you can see that as it is going on the right, the peak is going down, right. That is because of the dissipation in the upwinding scheme. So as it moves right, the peak will keep on going down. Okay, so that is what we are observing here. Okay, and if you depending on the CFL number and the delta t and delta x, you will have basically the peak may dissipate much more faster. Okay, so you can see that how much it has dissipated. Okay, now let us go and try some other scheme. Okay, let us try the central scheme. Okay, so we know the central scheme is not stable, but still let us try and see how it behaves. Okay, so you can see that now it is going above. okay, and you can see that this wiggles have started coming. Okay, I have limited it probably y limit of 0 to 1. Okay, I'll just change the limit and show it to you. Okay, so you can see that it has started developing oscillations. Okay, and let me just change this y limit. Let's see how it happens. Okay, so now it has gone beyond 1. Okay, and these oscillations started developing. Okay, and you can see that now they are growing. Okay, in this place, focus near the x axis of 0, 1, 2. Okay, and this will become bigger and bigger, okay, with time. Okay, because there is no dissipation in the central differential scheme to basically kill this out, and eventually you can see the limit axis it's going -6 and 6, and it keeps on growing, and now it basically it blew up. Okay, if you run it for a long time, you will not see anything. So this is how the central differential scheme behaves. Okay, let's go and look at the Lex-Frederick scheme. Okay, Lex-Frederick scheme, as we know, it is a very dissipative scheme. Okay, and that is observed here. You can see that how is it is attenuating. Okay, let me just fix the y limit here. Okay, okay. So now it was initially at up to 1. Now see how much it has attenuated. Okay, because of the dissipation in the Lex-Frederick scheme. Okay. So you can do one interesting thing. So in the Lex-Frederick, we know that the dissipation error, the leading term is 1 by lambda minus lambda, where lambda is the CFL number. So the dissipation is very high. That is what we have learned in the last class. It is because 1 by lambda terms becomes very high. So if you use a small value of lambda, let us say 0.1, the 1 by lambda becomes 10. So 10 minus 0.1 is basically 9.9. So let us try that. Okay, let us use the value of such a value that my CFL becomes 0.1. Okay, so for that you can probably use so my dx is 0.1. Okay, and lambda, let us say I want to keep equal to 0.1. Okay, so dt will become, so dt will become dx into lambda by c, dx into lambda by c. Okay, so that is 0.02. Okay, let us use the value of 0.02. Okay, and then you have to run it for okay, just run it. Okay, you can see that decay is much faster now. Okay, from the peak value, decay is very fast. Okay, that is because we have used the CFL number and the lambda value, which is very low, and that is why the dissipation is very high. Okay, let us stop it here and use our old value, okay, which is 0.1, and let us look at the last scheme, which is the Lax-Van Troff scheme. Lax-Van Troff scheme, we know that it has I mean we just add the right amount of dissipation in this to make the FTCH balance. Okay, so let us run the Lax-Van Troff scheme, and you can see that the amplitude does not go down. So this is the Lax amplitude. Look at the top of the curve. Okay, and then the amplitude is not really going down. That means it does not have any dissipation. Okay, it has some dispersion, as you can see that some wiggles are getting developed here. Okay, but it does not have any dissipation. Okay, so it is not dissipating. It may have very little dissipation at the higher order, but here you cannot see any dissipation here. Okay, now we will do one thing. Let us stop it here. Okay, and add some more dissipation in this. Okay, so how do we add dissipation? So in the Lax-Van Troff, your alpha is equal to lambda square. What if I use the double of the dissipation? Okay, this is 2 into lambda square. Okay, and then you try that. So this is not Lax-Van Troff, but I have a scheme which has added some dissipation, and the dissipation is higher than the lambda square value. Okay, then run it again. Okay. Okay. So, now you can see because we have added the higher dissipation, I am still using the lax Van scheme, but because the added dissipation is higher, then it is basically going on the right hand side and the dissipation is happening. It is convecting with the speed c, which is 0.5, and depending on the delta t, it is basically covering that distance in every delta t, but there is a lot of dissipation happening here. Okay. So, you can control the dissipation, and as you can see that if you have a high dissipation, all these things, the vehicles that were growing here is basically not appearing, right, which you would have been seeing in the left of the curve, that is not appearing here, right. So, that is the advantage of having dissipation, that if you have any problem or any vehicles that gets developed, you can basically that gets killed with time, okay, or that gets minimized with time. Okay. So, now let us show you some relative plots. Okay. So, here I will use this same example, but I will show all the plots together. So, I have some more cases. So, in the last one we only show the exponential function, but I also have the sine function here, okay, which is basically sine 2 pi k. So, I have seeing a travelling sine wave. So, the initial thing is 2 periods in a distance of 1 meter. So, this is lambda equal to 1 by 2. So, k equal to 2 pi by lambda, that is 4 pi. So, u x 0 is 2 pi k, right. And then you have this heavy side function. So, heavy side which basically you will have the curve going up, then discontinuity and then come down. Okay. It is like a box. Okay. So, let us try with the first one only and we plot all of these things together. Okay. Same value 0.1, L equal to 10, okay, dx equal to 0.1, and we want to see all of these schemes together. Okay. So, I have some more schemes also implemented in this: upwind, central defensing, lax Frederick, lax Vendroff. Then I have also beam warming implemented. Okay. This is backward, this is backward. Okay. This is one step beam warming. Okay. Then I also have implemented a 2-step McCormack and 2-step Richtmeier. Okay. Let us first see the schemes that is very common that we have seen earlier. So, here you can see that I am just calling all of these schemes and updating my value. So, my upwind is UUP, my central is UC, okay, lax F is ULF, okay, lax W is basically ULW. So, I am calling all the functions and storing in the variables. Okay. Mac is McCormack is UMac, beam warming is UBW, and Richtmeier is URicht. Okay. So, we have also have the analytical solution. So, let me just plot this value up to lax Vendroff. Okay. Okay. And what are the schemes that we have? We have initial value, analytical value, then upwind scheme. I am not plotting the central scheme because this is unstable, lax Frederick and lax Vendroff. Okay. Let us do up to this point. Okay. Run. Okay, this is an exponential function, lambda equal to 0.5. Okay. And you can see this curve probably better here. Let me open it here. Okay. So, I hope you are able to see my screen. Okay. So, this is my initial wave, the black one, okay, and this is the final solution. So, the one here on the top you see is the analytical solution, okay, in the black color, okay, and then you have this is the upwind scheme, there is a lot of dissipation. So, I am plotting at a particular time, okay. The lax Frederick is even more dissipation here, okay, because of the high dissipation that we have in the lax Frederick, okay, and that is why it is most stable also, but the lax Vendroff is maintaining almost like the analytical one. Okay. So, that is what we found here. Okay. Let me just call one more thing because the plot is not looking properly. So, this is just a setting for the plot, okay, so that I can see it more clearly. Okay. So, yeah, you can probably see it better now. Okay. Yeah. So, here this is the initial condition and this is the final one. Okay. Now, let us do it for the other cases. Maybe I want to do the include the beam warming also. Let us include the beam warming also. Okay. So, this is the beam warming scheme now. So, beam warming scheme also you see that there is very little dissipation, but one thing we are seeing here is the phase error. That means that your beam warming is actually traveling on the right side of the analytical solution. So, let me just blow this up so that you can see it properly. Yeah. So, this is the lax fan drop, this the black one is analytical, and the one in the cyan color is the beam warming, and you can see the beam warming has got some phase error because it is not in of course, I mean lax fan drop also has some phase error, but beam warming has much higher phase error. Okay. Let us look at some other function. Okay. So, let me change you to the sine function here now. Okay. So, the sine function is as we saw earlier. So, the sine function is sine 2 pi k, okay, which is basically sine 2 k. So, that is 8 pi k, right. So, and then we are putting it between some values. So, I will show you the initial profile also, and we have the analytical solution also, and let us see how it behaves. Okay. Different schemes. Okay. Okay. Yeah. So, this is a traveling sine wave. Okay. So, it has basically traveled here some point. So, you have this black one which you can't see because it is overlapped here as the analytical solution. Then you have the upwind, which is this yellow value, lax Frederick dissipation, high dissipation, and lax fan drop and beam warming are almost at the same place. Okay. So, let me just blow this up, and you can see here the black one is the analytical one, upwind, lax Frederick, and the lax fan drop and beam warming are almost the same place. Of course, beam warming is traveling little bit right. Okay. What is the value of lambda here? Okay, lambda is 0.95. Okay, let me change the lambda and let us use the value of 0.25. Okay. In this case, I can directly change the value of lambda. So, as I change the value of lambda, my dt almost immediately gets set. Okay. So, if I am changing the value of lambda, run it. Okay. Yeah, you can see this now. Now, lambda is very small value. Okay, I think 0.25 or so. Okay. You can look at the lax Frederick. Okay, it is completely dissipated. Okay, because of very high dissipation. Okay, the upwind also has dissipated more. Okay, but the lax fan drop and beam warming are almost similar. Okay, the one thing you should note here is basically these wiggles. Okay. So, this wiggles is because of the dispersion error that we have in the lax fan drop scheme. Okay. Lax Frederick is completely dissipated, beam warming also has some dispersion as you can see here, probably on the right side here. So, this side. Okay. So, this is the leading error. Okay. In the lax fan drop we have the lagging error. Okay. So, this is the effect of lambda. Okay. So, this is lambda equal to 0.25. So, as we discussed last time that lambda should not be very small if you are using the lax Frederick scheme because the dissipation will be very high. Okay. Finally, we use the let me change it back to let us say 0.5. Finally, I will show you the heavy side function. Okay. So, change the input to 3. Okay. So, 3 is this is my third input, which is the heavy side function. Okay, which is basically initially a box, and let me just run this. Okay. So, the initial profile is shown here, the black one. Okay. Okay. So, you can see that this dotted black is the initial profile and the solid black lines is the final analytical solution, and the upwind you can probably see it better if I zoom this in. Okay. Yeah. So, you can see here at the corner. Okay. So, the lax fabric I mean it has dissipated the most. Okay. Then we have the upwind, and then we have the lax fan draft. Okay. And beam warming is showing some oscillations here. Okay. So, the profile is as expected. Okay. And you have lot of wiggles here in the beam warming as well as in the lax fan draft. Okay, near the discontinuity. So, that is also expected, because at the discontinuity, if you do not add any dissipation, okay, it is going to show you this kind of behavior. So, if you are trying to solve a problem which has got shocks and all, in if you are using lax fan draft or the beam warming scheme, that will not work, because you will get a lot of this phenomena. This is called the Gibbs phenomena. Okay, at the discontinuity, you will have this kind of wiggles that will be coming. Okay. The final thing that I want to show you is basically the McCormack and the Richtmyer scheme, which are the two-step scheme. Okay. And as we have discussed that for the linear problem, it is like your lax fan draft scheme. So, let us see if we are seeing the same thing. Okay, I'll just close all these things. Okay, I'll only open this McCormack. Okay, and let's see how it looks like. Analytical. Let me close this initial profile also. Okay, it's done. I'm showing you for the exponential function. Okay, yeah. Okay, so now this is only the Richtmyer and the McCormack. Okay, so the black one is the analytical, and the Richtmyer is slightly different, because you know that it is using 4 values. It is a 5 stencil scheme in one step, and McCormack is 3 stencil. So, McCormack is almost like the analytical one. Okay, I wanted to show you compare with the lax fan draft. Okay, so let me put the lax fan draft also. Okay, use this lax fan draft also. Okay, so we have lax fan draft, McCormack and Richtmyer, lax fan draft, McCormack, Richtmyer, and of course you have the analytical one. So, let us run this section. Okay. Yeah. Okay. So, here you can see that your McCormack and the lax fan draft is actually on top of each other. So, that is why you cannot see the lax fan draft. Okay. If I blow this, I can probably show it to you, and the Richtmyer is this scheme. So, this is slightly different from the lax fan draft. Okay, let me just blow this up. Okay. No, so yeah, I mean the lax fan draft and the McCormack for the linear problem, they are exactly the same. So, that is why you are not seeing anything here. If I just remove this, okay, probably I will put this some markers here. Okay. Yeah, so you can see that it is just coming on top of the lax fan draft scheme. Okay. So, with this we will end the class today. In the next class, I will show you some I mean how these schemes behave when you go to the nonlinear problem. So, I will show you solutions for nonlinear problem, and eventually we will go to solving a proper Navier-Stokes problem. We will start with the Euler problem, and we will solve a shock tube problem in the next class. Okay. With that, we will stop today, but I will request you please go back and write these schemes, solve it, okay, and try to plot these results and get a feel of how these schemes work. Okay. So, that will be very, very important when you start solving your CFD problem. Okay. Thank you very much.